So I'd like to share some slides here. I'm going to talk today about the use of radar at Mars. I should mention that I am the US team leader for the Shallow Radar Instrument, which is an Italian instrument on board the Mars Reconnaissance Orbiter. Let's see, I'll put this into play mode here. Does that look good?
Yep, looks good.
Okay, great, thanks. The Mars Reconnaissance Orbiter, of course, has been at Mars in orbit since 2006. And the shallow radar is a sounding radar, sometimes referred to as ground penetrating radar, that emits a signal from the spacecraft. It goes down, impinges on the surface, and some of the signal goes into the subsurface and reflects off materials below the surface, and then comes back up to the spacecraft where it's recorded by the same antenna. For those who aren't familiar with radar sounding, think of it a little bit like a CAT scan. So you may be familiar with this medical device. CAT being computed axial tomography, where X-rays are used to produce an image of a object that is put into the scanner. So you take your CAT and you put it in the scanner, and then you get a signal from the surface of the object that's in the scanner. And you also get signals from surfaces in the interior of the object. So we effectively are doing the same thing at Mars, but of course you can't bring Mars to the scanner, so we brought the scanner, or SHARAD, shallow radar, to Mars. So this instrument, as I said, emits this radar or radio signal, and the majority of that impinges on the surface directly below the spacecraft, and it is reflected back up at the speed of light. You get a strong return from the surface, but you also get returns from layering, say in this case, in the polar ice cap. And so this image that you're seeing in this video is the interior of the polar cap as imaged by the shallow radar instrument on the Mars Reconnaissance Orbiter. So these sort of profile images that we sometimes call radargrams tell us about the properties of the interior of the polar cap and other regions of interest on Mars. As I mentioned, we've been in orbit since 2006, so we've amassed quite a volume of data to the point where we really can do a CAT scan of the polar cap. So these are 3D cutaway views into the interior, showing you a bunch of different features, including the layering, some of the troughs at the surface that have a history of having evolved with the cap. You can see those trough surfaces in the interior. We also are identifying known craters at the surface that are partially in the ice, as well as buried craters that we don't have any surface expression. So that's very exciting in that it helps us date the ice. These results really have been quite amazing. They've shown us a lot of the layering in the interior of these ices that are related to the last several billion years of Martian history, probably just a few million for the North Polar Cap. Maybe a few 100,000 is, or a few 100 million is how old the South Polar Cap's thought to be. And the radar shows very distinct features in the two polar caps. One of the more exciting ones, especially when considering ideas like trying to terraform the planet, is that we found extra Martian atmosphere of CO2 ice in the South Polar Cap. These features up near the higher parts of the cap here, pointed out here, these CO2 ice deposits, they actually amount to an entire Martian atmosphere that's kind of lurking just below the surface. But the radar doesn't just detect the polar caps. We observe all different portions of Mars, including some of the past landing sites. Somewhat frustratingly, we don't get the greatest of returns at the landing sites. In fact, the Phoenix landing site in the North Polar or northern plains region is really the only place we get a distinctive radar subsurface return. So this map on the left shows where we were able to detect these returns associated with ice. And the graphs on the right show a radargram at the top where we see these faint returns coming in below the surface return. The middle panel is where we've interpreted that layer with this yellow line here, the blue line being the surface return. And then the radar analysis can be complicated by the fact that the signals aren't just coming from below the spacecraft. They actually come from off to the side of the spacecraft. These returns we call surface clutter. They sort of clutter up the image. And so we have to do things like make a simulation of what the surface return only is. And then where we don't see things in these simulations, then we can more confidently interpret them as subsurface returns. I mentioned on that previous slide that we're not detecting the top of the ground ice, we're just detecting the base of the ground ice, or what we think may be the base of the ground ice. But why not the top of the ice? Well, it's very shallow. It's only a few centimeters to tens of centimeters down to the top of the ice, as was proven by the lander itself. Was able to scrape down and expose the ice. Whereas the resolution of the radar signal is kind of depicted here with this graph on the left, is very coarse vertically, about 10 meters or so of vertical resolution. So we can't really distinguish that top of ice from the surface return itself. Whereas the deeper return is potentially the base of the ice, although because of that resolution issue, it could be a return from a different interface at depth. So in addition to the polar caps and the high icy plains, there are these features down closer to the equator, say at 35, 40 degrees north, that we've known about for many, many years, since the Mariner days in the 1970s, called lobate debris aprons. And the morphology of these features from imagery has always been evocative of ice. They have flow-like features that are reminiscent of glaciers on the Earth. But for a long time, it wasn't clear whether these were mostly ice or mostly debris with a little bit of ice to kind of lubricate the flow. Well, the Schrad radar came along and found a very strong detection from the base of these features. Here's kind of a raw radargram here in delay time, that similar sort of profile view we're looking at for the polar cap and for Phoenix. Delay time being how the data is actually measured. And then you can convert to depth, assuming the material is made out of water ice, and lo and behold, you flatten out these returns below these sloping lobate debris aprons and get a very strong return from the base. This tells us that these are nearly pure water ice in bulk. But again, we don't see, we can't distinguish the top of the ice. And that tells us that that debris layer at the top is relatively thin, probably less than 10 to 20 meters, and maybe even substantially thinner than that. There are other places in the northern plains, such as Arcadia Planitia, that the radar has been quite effective in understanding subsurface properties as well. So this area has a number of these terraced craters that have formed over the millennia. And the cameras on MRO, their stereo imaging, allows us to establish what the depth of these terraces are in the craters. And then we can relate these terraces to other returns that we see in the Sherrod data. And then that allows us to constrain the material properties down to those reflective interfaces as seen in this panel below. And the result is very suggestive that these are contain a lot of ice, these upper layers. So this is what we call ground ice. And initially we thought that this might even be nearly pure water ice, but more recent analysis suggests, well, maybe the ice content isn't quite that high. It could be quite dirty ice. Nevertheless, these are huge deposits. They cover over 1 million square kilometers where we've mapped them out with radar. To give you a sense of scale, that's the size of California and Texas combined. And the latitude extent reaches down to about 38 degrees north. And this is getting into the zone where conditions are much more favorable for human explorers than say up at the polar cap or even at the Phoenix landing site up at 68 degrees north. So not as kind of the prior slide alluded to, we don't figure everything out with radar. In fact, we use as many data sets as we can to try to understand what's going on in the subsurface. And because of the interest in sending humans to Mars, NASA decided to fund an effort that was very much focused on looking for ice at the lowest latitudes we can find it, to serve as a resource for humans when they arrive. And this resulted in the gathering of a team of researchers that we refer to as the SWIM team, because we're doing subsurface water ice mapping on Mars. So the Mars SWIM team has combined these radar data sets with other data sets from various different spacecraft. The cameras on MRO, as well as the Mars Odyssey spacecraft, the neutron spectrometer data, which detects hydrogen in the near surface, hydrogen being associated with ice, water ice. And then the Mars Global Surveyor data, the thermal emission spectrometer on that spacecraft is very helpful, as is the MOLA Mars Orbiter Laser Altimeter data that tells us about elevations. So we kind of have these collection of data sets then that allows us to try to really constrain where these ices might be. And the areas that we were focused on for the first part of our study was these lower elevation areas all across the Northern Hemisphere. And so because these different data sets are telling you different things about the subsurface, it's a little bit challenging to try to amalgamate them together. So we came up with a scheme that we call ice consistency, where we rate each data set's contribution to whether or not its information is telling you that there is ice there or there isn't ice there. So in these map views of ice consistency, bluer tones mean, yeah, the data sets are pointing towards ice really being present here. Redder tones are like, no, there's probably not a whole lot of ice to be found in these regions. So this is a polar view with the North Polar Cap in the middle, and the the blue areas that surround the northern pole, we kind of expected that. That's in this sort of Phoenix zone and reaching a little further to the toward the equator, and then down into these low debris apron areas. But there are areas that extend much further south below this 30-degree mark, and these are getting really interesting for human landing site purposes. So if we cut away the reds, then you can kind of see the distribution of promising sites that we're getting from the SWIM efforts. And one thing that has helped us out a lot is there's the ongoing mission has been identifying fresh impacts on the planet. So we get before and after images, and some of these new impacts actually expose water ice. You can see the water ice on the ground, and they confirm it with spectrometer that it is actually water ice. And we were happy to see that the fresh ice exposing impacts line up quite well with where we're mapping likely presence of subsurface ice from these other instruments. So we're not done with this effort. Certainly, we're really kind of just getting started at this point here. In fact, the last year or so, the SWIM team has had our second season, and we recently completed that work. We extended our mapping down into the southern hemisphere, and also into some of the lower lying regions of Tharsis that's in this area here. And the exciting news is that we are finding a lot more areas of ice consistency and using the same sort of calculation as we did in the first season of SWIM. This new mapping is involving a lot more advanced methods in the geomorphic mapping, the thermal analysis, and the radar analysis. And these results are going to be available soon. We'll have a chapter coming out in a book about space resources that'll be out next year. And the products themselves, the mapping products themselves, will be freely available on the SWIM website, as the ones from the first season already are. So just to wrap up here, in general, the radar instrument it has been shedding a whole new light on our understanding of polar deposits and their connection to climate, as well as mid-latitude ices, and their interaction with the atmosphere and the Martian climate over the last many millions of years. The strong basal returns that we see from these low debris aprons that we can now confidently call debris-covered glaciers really demonstrated that their ice-rich nature, and that there's just a veneer of debris at the surface. So that's exciting from a ice resource standpoint. Elsewhere, these ground ices are also very extensive and could well serve as a ice resource for future human missions. There are some limitations. I mentioned the resolution of the radar. It kind of doesn't allow us to fully map all the details of where this ice is and what its concentrations are. So if we're really want to prepare the way for humans, we need to redouble efforts to locate this ice, develop new missions with more, finer resolution radars, for instance, and then get to the surface and take ground penetrating radar to the ice-rich zones and look for it at the surface. So I'll stop there, and I'd be happy to take any questions in the time remaining.
Yeah. Are there any plans to use this type of technology to explore the interiors of asteroids?
I'm not aware of any plans to do that with radar, but it's certainly a distinct possibility. Both from an orbital sense, and one could actually go to the surface of the asteroid as well. I do know that there are some studies to do similar kind of soundings where you actually put a receiver on the far side of a small body and look for transmission signals through to characterize the interior as well. One of the difficulties with the radar is you need, if you're doing it from a single, from one side like we do with the Mars radar, you have to have some coherent return from the interior, which usually requires some sort of layering.
Gotcha. What did you make of the high total electron content found by Shard on the Mars night side during the Siding Spring comet flyby in October 2014?
Right. So yeah, I didn't really go into that at all, but the radar tells us about the Martian ionosphere as well, the effects on the radar signal, and we use that to study how the ionosphere evolves over time. The Siding Spring comet came close to Mars to the point where Mars passed through the tail of the comet, and there was a distinctive effect on the ionosphere that was picked up by the Sherrod radar, and I believe some of the instruments on MAVEN also detected it. We typically confine most of our observing to the night side of Mars where the ionosphere is quieter, particularly when we're trying to do subsurface sounding, because the ionosphere does actually attenuate the signal significantly, reducing our signal to noise.
Gotcha. So you mentioned being able to tell the difference between CO2 and water ice, but can you actually tell the contamination of the ice, as in the purity of the water or how the salinity of it?
Yeah, to the extent that we have a good constraint on the, say the depth to the reflectors, we can place pretty close constraints on the dielectric properties, and then you can relate the dielectric property to the fraction of ice that may be mixed in with a material. And these techniques have been used for both the polar ices and these mid-latitude ices. The difficulty is getting a really good constraint on the elevation.
5 minutes left.
Have you been able to do any of the mapping of ice within lava tubes?
That's a great question. So one of the I mentioned the vertical resolution constraint on Sherrod, and the size of these lava tubes is actually quite large, as far as we can tell from surface imagery with Mars, maybe up to 100 meters or so. However, the lateral resolution of Sherrod is rather coarse as well, several hundred meters. However, there have been some indications in the data that we may be able to tease out a signature. So far, there haven't been any definitive publications showing lava tube detections with Sherrod, but stay tuned. I think that may change in the coming year or two. It's just kind of at the limit of our ability to resolve. If there's ice in the lava tube, then we may see a reflector associated with that. But again, it's going to be, touch and go whether we'd be able to resolve it.
Gotcha. Is there a way for you to determine other types of materials on Mars, i.e. like ore deposits, or is that not within the capabilities of the radar?
It certainly is a possibility. We definitely are mapping other material types. I didn't really go into that too much, but yeah, we were able to constrain dielectric properties, say for lava flows. So we understand the characteristics of different lava flows and ash deposits and those kind of features from the radar data. The radar data, though, on its own isn't going to distinguish between particular mineralogies, but in conjunction with other data sets, spectrometer data or morphological data, you can then sort of try to figure out what the most likely minerals are that are being detected.
Okay. Hi, Than. I've got a couple of quick questions. One is, could there be liquid water at the base of these glaciers, kind of a slick down there? And the second is, if you want to look for underground lava tubes and caverns, what kind of orbiter do we need? How should it be instrumented?
Those are great questions. You may have heard in the news that the other radar at Mars, MARSIS, was able to detect what they believe is a liquid water beneath the South Polar Cap, 1.5 kilometers down. If that really is liquid water down there, then it's certainly possible that up at these lower latitudes, we would be able to have liquid water underneath these glacial deposits. However, the charade signals that we're getting are not so strong as to be a clear indicator of liquid water at the base. And there are other morphological indicators that they're probably not wet-based glaciers, at least not by and large. The way they flow indicates they're more likely, dry-based glaciers. And then as far as, what new technology we need to, tease these problems out, like the thickness of that debris cover and the presence of lava tubes and the ice within the lava tubes, really a key piece of this will be a higher resolution radar. So something that's running in the several hundred megahertz range up to a gigahertz or so. It's going to reduce your ability to penetrate to greater depth, but it will allow you to resolve these shallower characteristics of these materials, including producing a finer lateral footprint. So you would be able to resolve smaller features like the lava tubes and some of these smaller glaciers, as well as the tops of the ground ices all across the northern plains. So yeah, I think it would be very critical to get an instrument like that to Mars as soon as humanly possible.